Earth's magnetic field isn't just a scientific curiosity, Bao. It's a crucial part of what makes life on this planet possible. Generated deep beneath our feet in the outer core, this protective force emerges from swirling molten iron and nickel nearly 2,000 miles below the surface. The constant motion of this superheated liquid metal generates electric currents, which in turn produce Earth's global magnetic field, a geodynamo that has been running for billions of years. This magnetic field creates what's known as the Magnetosphere, an enormous teardrop-shaped shield that extends tens of thousands of miles into space. Its job? To deflect charged particles from the solar wind and cosmic rays that constantly bombard our planet. Without this magnetic shield, Earth's atmosphere would gradually be stripped away by solar radiation, much like what happened on Mars billions of years ago. In other words, Earth's magnetic field is not just invisible, it's indispensable. But lately, scientists have noticed some unusual behavior. The most visible sign of this turbulence is the dramatic movement of the magnetic North Pole. For centuries, the North Magnetic Pole drifted gently through the Canadian Arctic. Then in the late 20th century, its speed began to increase. By the mid-1990s, it was moving about 9 miles per year. But by the early 21st century, it had accelerated dramatically to speeds between 34 and 37 miles per year, a rate 4 times faster than previous averages. Though that speed has recently slowed to around 22 to 31 miles per year, the overall trend remains clear. It's headed rapidly towards Siberia. This movement isn't just a scientific footnote. It has forced international agencies to update critical navigation systems more frequently. The World Magnetic Model, which underpins everything from smartphone compasses to military navigation tools, required an unexpected update in December of 2024 due to the pole's erratic sprint. But pole movement isn't the only concern. Earth's magnetic field itself is weakening. Measurements taken since the early 19th century show a decrease of about 9 to 10% in the field's global strength. And when scientists dig deeper into the geological record, they find that this decline may be even more pronounced, potentially a 30% drop over the last 3,000 years. One especially alarming feature is the South Atlantic Anomaly, a vast region stretching from South America to Southern Africa, where the magnetic field is significantly weaker. In this zone, satellites are exposed to increased levels of radiation and are more prone to malfunctions. The Hubble Space Telescope and other satellites often power down sensitive instruments when passing through it. This weakening is not uniform, it's patchy, complex, and hard to predict. The magnetic field's behavior isn't random, it's the result of shifting patterns in the fluid outer core. Scientists believe 2 large magnetic regions under Canada and Siberia are locked in a kind of subterranean tug of war, influencing the position and movement of the magnetic poles. Right now, Siberia's magnetic region appears to be winning, hence the rapid movement of the pole in that direction. While all of this may sound apocalyptic, it's worth noting that changes in the magnetic field are not new. Earth's magnetism is naturally dynamic. The problem is that we're now starting to detect large-scale changes over human timescales, not over millions of years, but over mere decades. And this opens the door to much deeper questions. What happens if the weakening continues? Could it signal an impending magnetic reversal? Could it affect our technology, our climate, or even our biology? That's where we'll head next. So now that we've broken down the weird behavior of Earth's magnetic field, let's talk about what's really on the line. Because while the idea of a magnetic field collapse might sound abstract, the impacts would be anything but. This isn't just a science fiction scenario. If the field continues to weaken or goes into a full reversal, the fallout could hit every layer of modern civilization, from satellites in orbit to ecosystems on the ground. Let's start in space. Satellites, which form the backbone of global communication, navigation, and surveillance, are extremely vulnerable to radiation. Earth's magnetic field acts like a protective dome, deflecting charged particles from the sun. Without it, or even with it weakened, those satellites are exposed to intense solar and cosmic radiation. This isn't theoretical. We already see it happening in a region called the South Atlantic Anomaly. In that part of the world, the magnetic field is so weak that satellites passing through it often experience memory glitches or suffer from electrical failures. Engineers have to program some satellite systems to shut down temporarily while passing through this zone to prevent damage. Now imagine that anomaly expanding globally. Without adequate shielding, satellites in low Earth orbit would degrade much faster. Global positioning systems, satellite phones, weather forecasting tools, and internet access through orbital networks like Starlink could all become unreliable or fail altogether. And these systems are no longer just conveniences. They run everything from international finance to emergency services and air traffic control. But the risks don't stop in orbit. Power grids on the ground are also in the danger zone. When geomagnetic storms interact with Earth's magnetic field, they can induce electrical currents in long conductors like power lines. Under normal conditions, the magnetic field buffers a lot of that energy, but if it weakens or if a reversal causes temporary disruptions in the field's structure, the energy from solar storms can surge into power grids with little resistance. A striking example of this occurred in March of 1989, when a geomagnetic storm, triggered by a solar flare, caused the entire power grid in Quebec, Canada to collapse. In less than 2 minutes, 6 million people were plunged into darkness. That storm happened under normal magnetic field conditions. If the field were weaker, a similar event could cause continent-wide blackouts, destroying high-voltage transformers that would take months or even years to replace. The economic cost would be staggering, but the human impact, hospitals without power, food supply chains disrupted, no communications, could be far worse. And then there's the biological angle. The magnetic field helps protect living organisms from genetic damage caused by cosmic radiation. With less protection, life on Earth, including humans, would be exposed to higher doses of ionizing particles. Over time, this exposure could lead to increased cancer rates and greater risk of developmental mutations in both humans and wildlife. While our atmosphere would still provide some shielding, high-altitude regions and areas near the poles, where radiation already penetrates more easily, would be hit hardest. Some scientists believe that during past geomagnetic excursions or reversals, early humans adapted their behavior in response to these increased radiation levels. There's evidence that ancient humans began using caves more frequently, potentially as a form of shelter from solar activity. In modern times, however, we depend on technology and global systems far more than our prehistoric ancestors did, and those systems are far more fragile. Even animals would struggle. Many migratory species like whales, birds, sea turtles, and bees rely on the magnetic field to navigate. They sense magnetic lines almost like a compass to guide them across vast distances. If those lines become distorted, these species could become disoriented, lose their migration paths, or stop reproducing effectively. Entire ecosystems could destabilize, especially in the oceans, where magnetic navigation plays a critical role for both predators and prey. And while some impacts, like atmospheric erosion, would take an incredibly long time to fully develop, they are not impossible. Scientists believe that Mars once had a magnetic field similar to Earth's, but after it disappeared billions of years ago, the solar wind began stripping away its atmosphere, turning it into the dry, lifeless world we see today. While Earth's gravity and remaining atmospheric pressure would slow that process here, a significantly weakened field over many thousands of years could open the door to long-term atmospheric loss, with consequences no one can fully predict. In short, the magnetic field isn't just a fascinating part of Earth's inner workings. It's a critical piece of the puzzle that makes life seem Kuro and civilization near possible. As it weakens and shifts, we're not just watching a natural process unfold. We're potentially witnessing the slow unraveling of protections we take for granted every day. So how do we know all of this is happening? How can scientists tell that Earth's magnetic field is weakening, or that it might reverse in the future? The answer lies in a mix of space-based monitoring, geological records, and some pretty remarkable physics. This part of the story is not about guessing. It's about hard data and long-term observation. The first tool scientists use is satellite data. Since the early 2000s, a number of satellites have been launched specifically to monitor the strength and structure of Earth's magnetic field. The most advanced of these is the European Space Agency's SWARM mission, launched in the year 2013. SWARM consists of 3 identical satellites, flying in formation around the planet. They continuously measure the magnetic signals coming from Earth's core, mantle, crust, oceans, and even the ionosphere and magnetosphere. These measurements are incredibly precise, allowing scientists to map how the field changes in both space and time. What they've found is consistent with earlier predictions. The field has been steadily weakening, especially in a large region stretching from South America to Southern Africa, known as the South Atlantic Anomaly. In just the past 200 years, the global magnetic field has weakened by roughly 10%. But within the anomaly, the weakening has been far more rapid. This real-time monitoring is only part of the picture. To understand what might happen next, scientists also look backward, deep into Earth's geological past. They do this by studying volcanic rocks, ocean floor sediments, and even ancient clay pots. When molten lava cools, or when sediments settle, tiny magnetic particles inside them align with Earth's magnetic field at that moment. Once locked in place, those particles become permanent records of the planet's magnetic orientation and strength. These fossil magnets can be dated using radiometric techniques. Over the past several decades, this kind of research has revealed that Earth's magnetic field has reversed many times in its history. On average, it flips about once every 200 to 300,000 years. The last full reversal, known as the Brunhes-Matuyama reversal, happened roughly 780,000 years ago. That means we are long overdue by historical standards, though the field does not flip on a schedule. And what's even more interesting is that magnetic reversals don't happen overnight. Evidence shows they can take anywhere from 1,000 to 10,000 years to complete. During this time, the field becomes disorganized and weakens significantly. Magnetic north and south can wander unpredictably or even appear in multiple places at once. And that's exactly what's concerning scientists now. Magnetic north has been shifting at an accelerated rate since the early 20th century. It used to move around 10 kilometers per year. Now it's racing across the Arctic at nearly 50 kilometers per year. This movement has forced regular updates to navigation systems, including the World Magnetic Model used by everything from smartphones to military aircraft. At the same time, complex computer models of Earth's core, powered by supercomputers and guided by satellite data, are showing signs of increasing turbulence in the outer core, where the magnetic field is generated. This turbulence doesn't guarantee a reversal, but it aligns with what we would expect to see in the lead-up to one. Some scientists believe we may already be entering the early stages of magnetic excursion, a short-term disruption where the field weakens and shifts significantly without a full reversal. To be clear, there is still debate within the scientific community. Some researchers argue that we are simply seeing a natural fluctuation and that the field could stabilize again. Others warn that the current trend fits the pattern of past reversals and should be taken seriously, but no one is ignoring it. In fact, global magnetic monitoring has become a top priority for organizations like NASA, the European Space Agency, and geological institutes around the world. These groups are constantly updating models and issuing data to industries that rely on accurate magnetic positioning. So while we don't know exactly when or if a full reversal will happen, we're watching closely. The warning signs are real, the data is solid, and the consequences, as we've already seen, could be massive. What comes next might not be a sudden flip, but a long, messy period of change, and we may already be in the middle of it. If Earth's magnetic field suddenly vanished or flipped completely, life would not end. But the modern world as we know it would face serious challenges. This isn't about fireballs or earthquakes. The danger lies in something invisible but powerful, radiation from space. Earth's magnetic field acts as a giant shield, protecting us from solar winds and cosmic rays. Without it, that radiation would have a much easier time reaching the surface. One of the first and most immediate effects would be in the upper atmosphere. The magnetic field currently helps trap charged particles in radiation belts high above Earth, keeping them away from the surface. If the field weakened significantly, the solar wind could strip away parts of the atmosphere, especially the outer layers that contain ionized gases. While this would take time, it could increase our exposure to ultraviolet and high-energy radiation. The threat is even more immediate for satellites and spacecraft. Without a strong magnetic field, satellites in low Earth orbit would be far more vulnerable to damage from solar storms. Communication systems, GPS navigation, weather tracking, and military surveillance all depend on those satellites. A strong geomagnetic storm, similar to the one that hit Earth in the year 1859, known as the Carrington event, could fry entire networks and cause global blackouts. That event happened under normal magnetic conditions. Imagine the damage during a field reversal or collapse. Astronauts would be at greater risk as well. The International Space Station is still within Earth's protective field, but during a weakened period, that protection would shrink. Without additional shielding, astronauts could be exposed to harmful levels of radiation. Space agencies would have to delay missions or invest heavily in radiation-hardened technologies. On the ground, power grids would also be at risk. Changes in the magnetic field can induce electric currents in long conductors like transmission lines and pipelines. During past geomagnetic storms, some power systems experienced voltage irregularities, transformer failures, and blackouts. In 1989, a geomagnetic storm knocked out power in Quebec, affecting millions of people. That was a relatively minor event. A weakened or chaotic magnetic field would make these disruptions more frequent and severe. Migratory animals would face confusion too. Many species, such as birds, whales, and sea turtles, rely on Earth's magnetic field to navigate long distances. Studies have shown that some animals have magnetoreceptors in their brains or beaks that allow them to sense magnetic fields. A sudden change or reversal could throw off migration patterns, disrupt breeding seasons, and even cause population declines. Air travel could also be impacted. Polar flight routes, which pass through areas where the magnetic field is already weaker, would be more dangerous during solar storms. Airlines might have to reroute flights to avoid increased radiation exposure to passengers and crew, which would lead to longer travel times and higher fuel costs. And then there's human health. While Earth's atmosphere still offers protection from most radiation, a weaker field would let more high-energy particles reach the surface. Over time, this could slightly increase rates of cancer or genetic mutations, especially in people living at higher altitudes or closer to the poles. While the risk wouldn't be catastrophic, it's something scientists are actively studying. One lesser-known issue involves the technology that depends on magnetic orientation. Everything from smartphones to drilling equipment to submarines relies on magnetic data. During a field reversal, magnetic north would shift unpredictably. Compasses could become unreliable, and navigation systems that depend on magnetic input would need constant recalibration. This would affect shipping, military operations, and even underground mapping. Importantly, the effects of a full reversal wouldn't happen overnight. The transition could take hundreds or even thousands of years. During that time, the magnetic field would likely weaken, fluctuate, and form multiple poles before finally stabilizing. But this slow process doesn't mean the impacts would be easy to manage. Our infrastructure, communication networks, and global navigation systems were all built during a period of magnetic stability. We have no precedent for how to operate in a world where the field is shifting rapidly beneath our feet. In short, a magnetic collapse or reversal wouldn't destroy life, but it would challenge nearly every system our modern world depends on, from power and communication to transportation and navigation. While Earth has survived many reversals in the past, the stakes are higher now than ever before. The question isn't whether the planet can endure it. The question is, are we ready for it? If Earth's magnetic field reversed or significantly weakened, survival would depend not only on nature, but also on how well humanity prepares in advance. While we can't stop a geomagnetic reversal from happening, we can take real, concrete steps to reduce the impact on our technology, infrastructure, and health. First, let's look at forecasting. Scientists are already tracking changes in the magnetic field with high precision. The South Atlantic Anomaly, a region where the field is particularly weak, has been growing and shifting westward. This anomaly poses increased risk to satellites and has drawn attention to the field's ongoing instability. With data from satellites like ESA's Swarm constellation and NASA's Magnetospheric multi-scale mission, researchers can monitor these trends and spot signs of an impending shift. However, predicting exactly when a reversal might occur is still difficult. Earth's magnetic field is generated by the movement of molten iron in the outer core, and this geodynamo is complex and unpredictable. Some reversals in the past have taken as little as 1,000 years, while others took more than 10,000. There have also been failed reversals, where the field started to flip, but returned to its original state. This variability makes it hard to forecast the exact timeline or intensity of a future event. That said, there are steps we can take now to strengthen our resilience. One of the most critical areas is satellite design. Engineers are already working on developing satellites with stronger shielding against solar radiation. Space agencies are also exploring ways to reroute or power down satellites during major solar events to reduce damage. Having backup systems and redundancy in satellite networks would also help maintain communication and navigation during disruptions. On Earth, energy companies are beginning to study how geomagnetic storms interact with the power grid. Some are installing sensors and early warning systems to detect sudden spikes in ground currents caused by magnetic changes. Transformers and high-voltage systems can be built with protections that allow them to shut down safely instead of burning out. In areas like northern Canada or Scandinavia, where the field is naturally weaker, these protections could be especially valuable. Airlines may also need to rethink flight paths. During periods of high solar activity, polar flights could be redirected to lower latitudes to protect passengers and crew from increased radiation exposure. This has already been done during intense solar events in the past, and similar protocols would likely become more routine during a magnetic reversal. In the field of public health, medical researchers are beginning to study the long-term effects of increased radiation exposure. While Earth's atmosphere will still shield us from most of the sun's harmful rays, the added risk may lead to updated guidelines for radiation limits, especially for pilots, astronauts, and people living at high altitudes. Portable radiation sensors and protective materials could become more common in certain professions. Even navigation systems, both civilian and military, would require major adjustments. Modern aircraft, submarines, and shipping vessels often use magnetic compasses as backups to GPS systems. A magnetic reversal would force designers to rethink those systems or rely more heavily on non-magnetic alternatives. Military planners would also need to recalibrate long-range missile systems and battlefield navigation tools that use magnetic orientation. Education and public awareness could play an important role too. A magnetic reversal would not be a global catastrophe, but it could cause widespread confusion. Accurate, science-based communication would be essential to keep the public informed about risks and necessary precautions. Governments could release guidelines on how to respond to power outages, satellite failures, or navigation issues caused by a weakened field. In the longer term, some scientists have even proposed large-scale, space-based magnetic shields, giant structures that could help block radiation at key points between the Earth and the Sun. These ideas are still theoretical, but they reflect how seriously researchers are taking the potential risks of a magnetic collapse. Ultimately, while a full magnetic reversal would bring serious challenges, it would not be the end of the world. Life has survived dozens of magnetic flips over the past hundreds of millions of years. The difference now is that human society is built on fragile technology. Our survival won't depend on nature, it will depend on how seriously we take the warnings and how wisely we prepare for what's coming. A magnetic field reversal may be slow, silent, and invisible, but its consequences could be global. The best way forward is not fear, but readiness.